And did you guys just hear that? It's recording is started now. I'm just going to go ahead and share my screen. Can you guys see my desktop?
Yes.
All right, perfect. Okay, so welcome, class meeting number 2. Once we complete this week, we'll be 1/15 of the way through this course. Congratulations. This is the point where you all laugh and clap and cheer because it's just one less week with me after this one. So at any rate, I did want to point out some of the things that I've changed here in Canvas. For the Project 1 introduction, I've added some more info. Then we'll talk about today's stuff. And then for Monday, there's sort of 2 assignments in Canvas, which are basically just places for you to upload as you start to follow along with some of the particular videos and create something of your own. You capture some screenshots of it, and we'll talk about that at the end. Okay. All right. So, but this is the outline for today. So let's go ahead to the Project 1 introduction page. I'm just catching somebody's sound, or maybe I'm echoing a little bit in someone else's. If you wouldn't mind muting.
Focused back extensions. I'm doing these, I'm depending on my ass and my ass only to bring you up. Squeeze like you're.
I think I figured out who it was. I just muted them. All right. So if you need to shout a question at me, just unmute yourself. But in the meantime, hopefully everyone can hear just fine. Okay. So again, welcome to 367. We're going to start Project 1 today. And so the name of Project 1 is called Generative Lattice. Right. We're going to discuss how to generate grids, lattices, trusses, and space frame systems in order to better understand how we leverage parametric design to develop what start off as pretty dumb, sort of bland blank surfaces into a set of architectural components, right? So, you know, again, it's amazing sometimes I see these really silly sort of like planes, and they're meant to be like, you know, windows or walls, right? We all know that those sort of those parts of architecture, walls, windows, floors, you know, curtain walls, they're all made up of lots of small parts and pieces, right? And so, you know, I think that's the sort of mindset and the shift in gears in your head that I want you to sort of understand here, is that we're these things these tools can really augment the sort of process of getting past sort of architectural diagrams and into making actual material architecture, right? And so, and all of those things have to be composed, ordered, and designed and drawn, right, in order to sort of convey to the folks who make this stuff and assemble it, right, where it goes and what they need. So we'll learn the basics of parametric modeling through this project. So we'll start to place some nodes and match things up. We'll learn about the flow of information from left to right, how we make changes and add variables, and we change those variables, and the changes propagate and flow from left to the right and propagate through the model, the graph. So we'll put together a graph or a file in Grasshopper. We usually call those graphs. They look like these sort of mind maps, tangled balls of spaghetti, where each operation that we do, each tool that we would hit on the toolbar in Rhino, so it'll become a node in Grasshopper, and then we start to direct the flow. The output of one node becomes the input or ingredient for the next node, right? And so in that way, we start to program. We talk about data and data matching, how we manage not just to make something from one object, but lists of objects, and how we can begin to deal with lists and data trees and various ways that we store and organize information, right? So in this case, we're going under the hood, right? And sort of understanding how our software is actually organize and structure the information that we generate and then use. There'll be a healthy dose of geometry. Don't worry though, I think it's mostly accessible and not too bad here. And then we'll also talk about, in terms of geometry, the main ingredients that we'll be using this time around are points, lines, and curves, right? And so we'll start to look at how we generate those, and you'll roll your eyes because it's so silly and easy. But then we'll start talking about the parametric space that points, lines, and curves sort of contain. And then last, you know, the outcomes will be a sort of set of diagrams, drawings, and renderings of our system as we start to think about it as it becomes spatialized, and we begin to think about immersing ourselves and other scaled figures into these sort of renderings and drawings of the system that you create. Okay, so there'll be tone-based monochromatic drawings and renderings. So we'll mostly be looking at how to generate line work, how to take very simple tone, soft shadowed white clay model renderings, and compositing those things together, and then layering up in Photoshop some spatial collages, right? So oftentimes, when it comes to these sorts of things, when you're digitally modeling, the question pops up in your head, all right, well, what issues and problems do I try to tackle through rendering, and what issues can I address and tackle through post-production in Photoshop and Illustrator? And oftentimes we lean more towards the Photoshop and Illustrator side because things look better and you can make things more intentional, and you're not fighting so much, and they're less computationally intensive. So we'll go through several, I think, helpful workflows over the semester to take not only these complex models that you generate, but then to sort of talk about the design communication side of things when it comes to generating drawings, diagrams, and perspectives. All right. And so in this case, we'll be looking at diagrams, axons, and perspectives. So the objectives for the project to demonstrate an understanding of algorithmic thinking, and we'll talk about algorithms and what algorithm thinking means today, as well as procedural design or procedural drawing or procedural modeling. Again, that's what I want to address with you guys today in the lecture I give here shortly. Along with applying your understanding using a parametric software, in this case, Rhino and Grasshopper, and then we'll be using some Illustrator and Photoshop. We'll also talk about understanding and begin to design the relationships and associations between various pieces of geometry in these sort of larger lattice and truss systems that we create, right? So, when we're talking about trusses, we're talking primarily about structure and sometimes building envelope. If you turn these things vertical, then suddenly they can withstand lateral loads for holding up glass and curtain walls and things like that, right? Or if you turn them laterally, then they become sort of spanning. You put floors and roofs on top of them, and they're withstanding gravity and people jumping up and down on them, and placing stacks of and shelves of books and bathtubs full of water and everything else that we do, to crazy things that we do to architecture that has to withstand with gravity loads, right? So, but when you think about structure, right, there are rules and relationships between, let's say, how far you span and how deep a beam needs to be and how beefy it is, right? And you guys will start to learn these things this year, actually, in structures course. But what you'll begin to understand is that there's a set of parameters and variables, right? And what's really important is a sort of set of laws and relationships between them, right? And so you start to understand that there are general rules of thumb between how far you span and then how deep your structure needs to be, right? You also understand when we're dealing with, like, let's say, steel tubes, both round and square tubes and rectangular tubes, there's thicknesses and depths and sort of the robustness of the cross section of these shapes, and becomes directly related to what they have to withstand, how they have to perform structurally, right? And so this is our first taste at sort of looking at both aesthetics and performance, in this case, structural performance, and beginning to sort of understand how that relates back to geometry and some of the associations between geometry, right? So we can start to look at the length of a truss and start to, take every foot of that, convert it into inches, and then add 6, right? And then suddenly we have a structural depth. Or, we can begin to sort of look at the diameter of pipes when it comes to those cords and say that they're all going to be twice as large as the webbing diameter, right? And so again, these sort of relationships are something that we can build into the model. So then as we start to adjust things and change things, everything sort of really intelligently starts to update along with it, okay? So that's what I mean when we start talking about complex models. We start to build in all of these interdependencies, right? So that when I start to move one slide bar, right, the rest of the model reacts in ways that save you time and begin to optimize the result, all right? So, and it's really exciting, and some of it's kind of exciting, some of it's kind of boring, and some of it's just really hard to understand, but we'll get there, all right? To understand the internal parametric properties of points and curves. So we'll be diving into the geometry of points, lines, curves, talking about them, and more on that over the weekend and then into next week. To develop a computational literacy for key concepts and procedures in computational design that can be applied to many different projects regardless of the platform. So we'll be going over things like parameters, variables, lists, rules, looping, repetition, data matching, all these things that your software will do for you, or that you would need to know anyway if you're going to program or write a script. And so, just as we interrogate our tools like pencils and X-Acto blades and things like that, right? And sometimes we use them the way they're intended. Sometimes we misuse them the way they're intended. We can do the same with digital tools, right? We can get under the hood. We can customize them, right? And that's what this course is all about, is making the software work for us instead of us working for the software, right? So, a software developer shouldn't be telling us how we should be using the tools, but rather there should be a nice conversation where we can begin to shape our tools ourselves. And so software I would include in that, and that's what we are doing. Let's talk about some key terms before we get into the lecture. So, not to beat this, not to beat a dead horse here, but there are some key words here, and these should all be, I sure hope they're all familiar to you. But just in case this wasn't hammered home to you in last year and second year studio, what do I mean by form? So I say, interesting sort of formal studies here, or the form of that seems really simple, or the form of that seems really complex or complicated. What do I mean by form? Anyone? The shape, right? I'm talking about the shape, right? So when we're talking about the form, we're looking at the overall shape and our reading of it, right? For instance, if I would compare the architecture building here at UNLV, USNLV, somehow I forgot which institution I work at, but anyway, if I was talking about the form of the School of Architecture here, the wing with all the studios and offices and workshops and wood shops and metal shops, I basically call that a shoebox. It's basically a rectangle, right? And then, the library is like this sort of weird octagon and plan that's sort of extruded up with some weird roofs on it. And then where those two things slam together, right, we place the entrance. And then there's like a sort of triangular wedge, right? So if I was describing the form of this building, it'd be actually quite simple. I'm sort of saying, well, we have a sort of shoebox over here, we have an extruded can over here, and then we have a triangle sort of connecting the two, right? Lots of right angles and a few non-right angles, nothing curvy, nothing weird in that sense. What do I mean by order? What I mean is how we arrange things, right? The sort of opposite of disorder or chaos, right? And so our jobs as architects are to bring, order to things, right? And so, I think that's really important and to say, right? Because, how we order things, the relationships to each other, the hierarchy that we establish, right? The sequence or the cadence or the patterns that we create, right? Are super important, and you see them over and over again repeated, right? There are things called ordering systems, which is the next item, right? Which is the sequence or pattern of the sort of systems that we use in order to bring order to things. Of course, it's no surprise, right? Let's not overcomplicate this. You see these every day, right? Grids is probably one of the most common ordering systems that we use, right? And we use them at so many different scales. I look down at my office carpet, or I look down the hallway floor and I see a grid, right? I look on the walls where I see masonry and I see a grid. I look at the structural system of the building, I see a grid. And a lot of them are like that. Some of them, aren't just rectangular grids or square grids. Sometimes they're radial grids or conformal grids or distorted grids or two grids rotated against each other, right? I zoom out even further. I look at the cities. The cities are arranged in grids, right? Okay, and on and on and on, right? So we understand this. We even look at latitude and longitude on the globe. Again, a grid, right? There are other sorts of ways of thinking about, their grids. There are linear sort of ordering systems like axial ordering systems or spinal ordering systems. There's sort of less hierarchical systems where you start to get branching ordering systems, etc. Right? So let's just delve into this grid. I don't think it should be anything hard here, but a network of lines or curves that cross each other, right? They form a set of cells. Sometimes it can be regular cells or irregular cells, depending on what we're doing. All right, let's get to the word lattice, because that's in the name of the project, generative lattice. So a lattice is a structure consisting of strips of struts and joints that are crossed and fastened. Sorry, I'm not talking very well. A structure consisting of strips of struts and joints or nodes that are crossed and fastened together, and they leave squared or diamond-shaped spaces left between, right? So that's the Oxford Dictionary definition of a lattice, or an interlaced structure or pattern resembling a lattice, right? What I mean is, and I think the third definition sort of really maybe paints a picture in your head that a sort of visual picture that's helpful. A regular repeated three-dimensional arrangement of atoms, ions, and molecules in a metal or other crystalline solid, right? So remember back in high school, maybe even some junior high, you would study atoms and molecules, and you would start to see these molecular models, right? They're lattices, right? Each atom was a node, and then there were these sort of bonds in between things that were the sort of struts, right? And so if you think about a lattice, right, we sort of think about these sort of three-dimensional crystalline structures consisting of strips and nodes, or struts and nodes, or struts and joints, right? Now, if we think about that two-dimensionally, a truss is like a two-dimensional lattice, right? It's contained within a singular plane, a structural framework with struts, the chords running along the tops and the bottoms, as well as the bracing or webbing, right? Are all sort of interconnected. Sometimes they're welded, sometimes they're pinned or hinged or bolted, but they're used to sort of span longer distances, right? Okay, so we see them on bridges oftentimes. When we go to like big warehouse structures where they want to try to avoid putting a bunch of columns in the center of it, right? Then what they'll do is they'll beef up the walls on the outside and they'll span with trusses across, from one end to the other. All right, so truss is like a two-dimensional lattice, right? That works as if a sort of long span beam. And then for space frames, they're three-dimensional trusses, right? So three-dimensional lattice or structural framework, like a three-dimensional truss made from struts and braces, but then you have cords going in both the X and the Y direction, so to say, and then webbing connecting in the Z, right? Sort of going back and forth. All right, so if you've never seen space frames, this would be a helpful Google search. Oh, what in the world? Space frame. All right. So we go to images for space frames. You can see, right, there's a good example of space frames. In fact, you go to the Student Union, there's a space frame outside in the plaza, right? And then they hung, it looks similar to this, except it's painted white. And then they've hung cloth shade structures in between, right? And so you can see that, sometimes they form a regular square or rectangular grid. Sometimes they're conformal grid that sort of stretch across a doubly curved surface, right? But nevertheless, right, we can see these sort of three-dimensional trusses, right? These space frames. Sometimes they're made for canopies and roofs, right? To span three-dimensionally across an entire space. Oftentimes you can see these as part of the envelope of a building skin, right? So in this case, you have a long expanse of glass, like a window wall. So what's holding it up is a space frame in this case. Okay. All right. And so I just wanted to make sure that we're on the same page here. And you can always go back and look these up in the Project 1 introduction. Okay. I'm going to go back to the modules and let's talk about what we're going to do today. Yay. All right. So again, I recommend when you're using Canvas, just to go to the modules. Project 1 is the first module, the first real module with lots of stuff in it. 25th of August, algorithms, procedural modeling. Okay. I think it's really important to say that date is there so that if you want to figure out, well, what you want to try to remember what we did on August 25th, right? On this page, I'll also be reposting or posting the recording of this course session and lecture, right? So today we're going to talk about algorithms and procedural modeling. We're going to start in the art world, and we'll start simply with two dimensions. And in this case, we'll look at wall drawings by Solowit, the artist. We'll take a look at these sort of procedural wall drawings that he did as a set of series, right? And then we'll look at those and we'll start to think about and talk about this sort of idea of algorithms, right? I think that's really important. A classical example of conceptual art, these wall drawings utilize a set of simple ingredients, a simple set of instructions, and then repetition, right? To direct a team rather than the artist in the creation of a large complex drawing. So that's the interesting thing about conceptual art. We'll talk about that in a moment, but the lecture slides are here if you wanted to follow along. But this is what we're going to be talking about a lot in this project, right? Points, lines, and different sorts of curves. And we'll be talking about them in terms of NURBS. We'll be talking about them in terms of geometry. We'll be talking about them in terms of their own parametric, internal parametric logics. Okay. I'm going to go ahead and start with the lecture, and then we'll come back to this and we'll talk about the assignment for Monday when we come back over the weekend. Okay, so you will have an assignment. There'll be a set of videos to watch over the weekend. And then at certain key times, you'll follow through and actually follow along with some of those videos. Okay. All right, so just kick off with let's talk, and I'm just going to go to full screen mode with my PDF. Can you guys see my slide still? It says Project 1, the parametric capacity of Solowit's procedural drawings. So yeah. Solowit was an artist in the 20th century, and I don't think he's still alive. Maybe he is, I don't know. But he was a conceptual artist. The idea of conceptual art was that there is a set of ideas behind the actual art piece. And those ideas were more important than actually seeing the hand of the artist, right? So she or he, the artist, could indirectly make the piece of art without ever even touching it or shaping it themselves, right? So Hans Breeder, for instance, had a set of acrylic sort of sculptures, in which case all he did was develop the idea, develop a set of drawings, and then call the fabricator and give the instructions over the phone, and then have everything set up without even touching the piece. It would be set up in the museum. And in this case, Solowit, his wall drawings, these procedural drawings, right? All he left were basically just a list of procedures, right? For a team of other artists or draftspeople to execute on their own. And so let's talk about this just for a moment. Let's talk about this idea of procedural drawing or procedural modeling and algorithms, right? So these procedures, these step-by-step instructions are what we typically call in computation an algorithm, right? And that's essentially what it is. If you think about an algorithm, it's kind of like a recipe, right? So for instance, I don't want you to overthink this or be scared of the word algorithm, right? How many of you learned long division? Where you actually put the bracket in and you put the numerator on the left and the divisor on the right, and or I forget which one is which, right? And then you go through and you figure out how many times this one will go into this one, and then you write that down. The remainder you write down below, and you do some subtraction, and then you continue, right? And you repeat. That is an algorithm, right? That's just a step-by-step set of instructions where you take a set of ingredients, you perform those operations, and you get an outcome, right? And that's essentially what an algorithm is, a recipe. Here's another one. How many of you have cooked baked cookies? Yeah, now I'm getting hungry because it's almost lunchtime, right? Following a recipe is again kind of like an algorithm, right? You start with a set of ingredients, and then you follow the step-by-step instructions. It might be mix this, this, and this in a bowl, preheat the oven to 375 degrees, add a sheet, add another sort of tool, blah, 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 dip these things out on the pan, put them in the oven for a certain amount of time, take them out, let it cool for a certain amount of minutes or whatever, right? So we start to understand that there's a sort of an algorithm to these. And so again, oftentimes, right, we start with a simple set of ingredients. And so here's an example of an algorithm. Now, what it's making is just sort of a pattern, right? But what's the ingredient? It's just a square, right? The shape, a polygon. And then the steps are, I'm going to make a copy of this polygon. I'm going to rotate it 30 degrees. I'm going to scale it up by 110%, so 10% larger. And I'm going to repeat 1, 2, 3, 4 times. And that's what I get, right? Now, that's an algorithm in order to create, in this case, a pattern based off of rotation and scale, right? Yeah, simple, right? And we start with a very simple box. Now, those are the steps, right? Now, notice that I can rotate 30 degrees, or I can rotate 15 degrees, or I can rotate 10 degrees, or I can scale up by a little bit, or scale down by a little bit, or scale up more, right? And I can use the same set of rules, but I change those parameters, right? Those variables, right? The numbers, how much to rotate, or how far to scale, right? And then and then I get different results, even with the same ingredient and the same set of instructions, right? So those variables or those parameters, right? When those, I guess I should say when those parameters become variable and you change them, alter them, right? Even small changes to the parameters can sometimes lead to disproportionately different results at the end as a sort of an outcome, right? And so we can take this further, right? We have a step-by-step set of instructions. Let's look at this, right? So steps, rules, ingredients, and parameters. And this is really the sort of the meat and bones. These are the 4 things you need to make an algorithm. And so 4 things you need to start to think about the logic of parametric design, right? So let's break this down. The steps. First we copy, then we rotate, then we scale, right? Well, that seems pretty simple. Sometimes we have rules like, once I'm finished with these steps, repeat and loop around and perform them again. Let's say 10 times or as many times as you can until you run out of paper, or whatever those rules are, right? You can begin to set those. Okay. Ingredients, right? So in this case, we know we need a piece of geometry to operate on. So in this case, it's a polygon, right? So we need a piece of geometry in this case. To make a line, what are the ingredients? Oftentimes we need, well, let's say a start point and end point, and then we connect them up. The shortest distance is a line, right? And so I think oftentimes I don't want to bore you to death, right? This seems kind of obvious, but it's worth saying and making sort of explicit here, right? Because when things do get a little more complex, then I will start asking, okay, well, what are the ingredients here? What do you want as an outcome? All right, and then figuring out the steps in between to get from point A to point B. It's not obvious, and it's not necessarily a done deal in your head. You have to sort of draw these things out, sketch them out, and sort of work at them, okay? Right, we also know that we need to scale, copy, and rotate. We need a point to scale or copy or rotate about, right? So that center of rotation, or that center of scaling, or that center of moving, or whatever it is, okay? And then the parameters, right? These are usually numbers that we can change, right? They can become variable, right? So how much we rotate, 20 degrees or 30 degrees or 180 degrees, right? Or scaling, right? Do we want something to go half the size, in which case we scale by 50%. We want things double the size, we scale things 200%, right? Or when we're moving, right? How far do we move? In what direction do we move, right? Those are parameters, right? Or how many times we repeat the rule, right? How many times we repeat? Maybe it's 30 times, maybe it's 50 times, maybe it's 10 times, right? Repeating twice looks kind of silly. When we repeat more than twice, right? We start to get all kinds of different results, right? So here's repeating it 10 times. Here's repeating it with also adding another step, right? In this case, mirroring in order to get some bilateral symmetry. In this case, it's one extra step where we move each time the copy instead of so it rotated around the moved point each time in order to form a sort of a field of a sort of gradient grid-like organization here, right? So each of these come from the same algorithm. We're just creating variations on the algorithm. We change an input, right? We change a variable, or we change or add one step, right, to the mix, and we get different results, and sometimes very different results, right? Here's one where, you know, it's how many times you repeat and then adding some rules, right? Here's another one, right? Just the number of times to repeat, in this case using an S-shaped spline. I don't know how useful this is. It's kind of beautiful as a drawing, as a piece of art, but otherwise, you know, I don't know architecturally why you'd want to make your computer look like it's growing hair or something. That's what these things sort of resemble, right? So let's get to the conceptual artist Sol LeWitt, right? So he did these sets of studies, right, where he was really sort of, I think, interrogating, you know, and asking, as all good artists do, you know, what is art, and how is art made, and who can make art, and what does art mean, right? And you know, those 4 sort of existential questions of art, right, that everybody always asks, nobody can really answer, or everybody has their own answer to. But Sol LeWitt was really interested in these sort of pulling the rug back and sort of thinking about these ingredients, right, like line and shape, edge, and sort of thinking about them in terms of fields and grids, right? And so one of the things that he did was to start to develop a sort of set of logics. So in this case, this is a drawing called Straight and Non-Straight Lines, a study of lines and density, right, and pattern, right? So you can see that every other line is straight And then every line in between, those straight lines are not straight, right? Or purposefully purposefully and intentionally not straight, right? And so you can begin to see, again, with a study and enough repetition, enough of these, right? You can begin to see a sort of logic and a pattern emerge that's both regular and irregular, right? Which I think is pretty interesting, right? Here's another study of sort of non-straight lines, but in a sort of sequence of going from less dense to more dense, right? And not only that, when it comes to the number and spacing, but then non-straight and then less, straighter and then less straight, right? So, these don't deviate as much, these deviate quite a bit, right? These don't deviate as much, these deviate quite a bit, right? And so you can start to see non-overlapping versus overlapping, etc., right? And again, very, very simple, very, very simple steps, very, very simple rules, very simple ingredients, right? And yet, when you start to add the repetition, the sort of, you start to get this sort of variety, you start to get this, you don't see those individual things, right? It's like seeing the forest rather than all the individual trees. You know that expression, miss the forest for the trees. In this case, what we're looking for are these sort of interesting effects that suddenly you start to see a cohesive field sort of work of art rather than all the individual ingredients, even though the ingredients are quite simple, just non-straight lines or curves, basically, right? So then I think what's interesting is that LeWitt started to play around with these sort of wall drawings. In other words, these drawings or these instructions that could be done at a museum or a school by a set of artists or draftspeople in order to make the conceptual art. And so these wall drawings exist in several different locations, depending on who does them, right? But what's interesting is that it's basically, and each time these like the same wall drawing is done, it's different, right? And so I think that's some things I want to talk about here. So in this case, let's talk about these and let's look at the instructions and let's look at the results. And then we can, I think, have a better conversation about these. So for instance, wall drawing number 51 by LeWitt, this simplest set of instructions, all architectural points connected by straight lines. Okay, and so if you go to a museum wall with a wall drawing number 51, it might look like this, where they take a chalk line, you can see the blue chalk lines, and then they connect. Let me see if I can get my Zoom annotate tools up here. Here we go. I'll just draw on the screen for a moment. And so what they'll do is they'll identify every architectural point, right? Every point where they violated the wall with a fire alarm pole or flare, an exit sign, a corner of an entrance, right? A place where they put a kick plate, where the beams slam into the wall, where the beams in the wall meet the ceiling, etc., right? All of these points, each of these points is connected to every other architectural point, right? And so then what happens is, let's start with this point. It gets aligned to all of these other points off in space here, and it looks like there's a number of them that's that aren't even contained within the paragraph or the photograph, right? You can start to see what this means, right? It starts to build up a sort of interesting field along the wall where you start to sort of see a network of curves, almost as if you're looking at a sort of transportation map of shipping trade routes or flight paths or something like that. And I don't know if you're like me, a geek that actually looks at the magazine, the in-flight magazine on airplanes. And oftentimes at the back, they have all these sort of flight patterns where you can start to see basically the flight paths start to render the sort of bigger, larger places or airports that are the busiest, in the United States, JFK and LaGuardia and Newark, that sort of New York area, Atlanta, Denver, Houston, LAX, et cetera, right? And so, it's an interesting sort of way to sort of read the architecture in this case through art. Just go ahead and clear that out. Okay. Let's move on to the next wall drawing here, right? Wall drawing number 46 was, and this is a very simple set of instructions, vertical lines, not straight, not touching, covering the wall evenly, right? So vertical lines, not straight, not touching, covering the wall evenly. And so what you get is a close-up, right? Is you start to make a set of lines that are all sort of around the same length, or most of them are around the same length, right? And then you start to infill in between, and those get shorter, right? And then to infill in between, those get shorter, and then infill in between, those get shorter. But each time you're sort of trying to provide, even though there's no repetition to this and no symmetry, there is a sort of even distribution of lines, right? You're trying to sort of even out the density while still making a bunch of vertical lines not touching, right? Not straight. And so what's interesting is it starts to resemble a sort of grain-like pattern on the wall, right? Over a large space. Very simple rule, right? Very simple instructions, very simple ingredients, right? Here's another one. This is wall drawing 138, circles and arcs from the midpoints of 4 sides, right? And then, you would get these wall drawings where you start to get this sort of weird sort of parallax. You start to get things that converge and then diverge again, right? These arcs and circles, right? And where they converge, they start to converge in points, and then they start to diverge. You start to get this moire effect, this pattern where things start to look like they start to swirl. They look dynamic, even though they aren't. They're static sort of circles, but they're all sort of rotated against each other and overlapping in interesting ways. And again, what's interesting is they, along certain axes and in certain moments, they actually all align, in different places at points, right? They coincide. But most of the time they're diverging from those, right? Here's another one, wall drawing 86, right? So again, we're just talking about very simple two-dimensional pieces of art, right? But again, this idea of an algorithm or procedures, right? A very simple set of procedures, right? In order to generate sort of a larger, more complex composition, right? And that's what we do as architects, but spatially, I would argue, right? All right, so wall drawing 86, 10,000 lines. I wouldn't want to be the one that has to count them all. About 10 inches long, covering the wall evenly. Right? So you get something that looks like this. It doesn't matter if they're overlapping, it's just straight lines, and then making sure that you're sort of, you start in different places around the wall, and then you start to fill in, right? And then over time, you start to, again, try to even things out in density, right? 10,000 lines, right? So 10-inch line, straight line, right? That's not a very interesting, element or ingredient, is it, right? But then when you place them all over the place and you have enough of them, right, you start to get a different reading. Here, I don't see 10,000 lines. I start to see a pattern and a texture, right, which I think is really interesting. When you zoom out further, you start to get more and more of just the texture. All right, here's wall drawing 797. This is a very famous one. This one's a little more involved, right? But again, it's an algorithm. It's a step-by-step set of instructions. The first drafter has a black marker and makes an irregular horizontal line near the top of the wall. So it makes a horizontal line across the wall, but an irregular one, so it's not straight. Okay, then the second drafter tries to copy it without touching it down below it using a red marker. The third drafter does the same using a yellow marker. The fourth drafter does the same using a blue marker. And the second drafter followed by the third and fourth copies, the last line drawn until the bottom of the wall is reached, right? So this is like an offset command, right? And that's kind of what it looks like. Depending on what that top one was, then everything sort of offsets from it. And then it's all about being really careful and trying to sort of follow the steps and not accidentally intersect anything and just sort of, repeat over and over and over again, right? Each time these are done, they're different. Now they look similar, right? But they're each influenced and informed by the people making them, right? In the situations, the dimensions of the wall, etc., right? And so that first curve sets all of the rest of the wall drawing into motion, right? As far as what it will look like. All right, here's another one, grids and arcs from 4 corners, very similar to 138. This is 130, right? And again, the places where things align and don't are sort of different, but it's again very much akin to 138. Right. Here's another one, some more. These are studies from a book. Looking at these studies, you can start to see that moire effect, right, where you get two grids sort of overlapping, but not quite, and over, rotated against each other, right? It's kind of an interesting visual effect called the moire effect, M-O-I-R-E. You can start to see different different densities, right? And different readings, different samples, you get a certain quadrants versus the whole thing, right? The center points in the center of the page, or if the center point for all the arcs are on the edges, right? You start to get different readings. Here's one called 118. On a wall surface, any continuous stretch of wall, using a hard pencil, place 50 points at random. The points should be evenly distributed over the area of the wall. All of the points should be connected by straight lines, right? So each point gets connected to every other point, right? And that's what these things typically look like, right? All right. Now, what's interesting is I'll show you some examples of these on Monday and Grasshopper. They're actually quite easy to make because it's an easy algorithm, right? And so making these in a parametric design software becomes almost trivial. It's quite easy to do, right? I won't make you guys do them, but I did just want to sort of bring this up as again, I think an easy, visual, accessible way to start to understand what I mean when I say algorithm, procedural modeling, and in this case, you know, we have these wall drawings. Now, what happens when some of these turn three-dimensional? They start to become lattices and trusses, right? They start to become sort of three-dimensional fields, which I think could become very interesting. Okay, all right. Okay, you guys still with me?
Yep. Yes.
All right, great. I don't want to lose any of you. So on Monday, I promise, remind me. I'm happy to open up Rhino and I'll show you some examples of these. But on Monday, what we're going to do is I'm going to look at the results of what you did. We're going to talk about the work that you do by watching and then following along with some of these videos, right? I know there's 14 of them. So what I recommend is just sort of trying to do several of them, you know, sit down for an hour and do a few of them, right? You know, next day, sit down for an hour and try to do 4 more of them, right? And then, you know, Saturday or Sunday, you know, spend an hour or two just, you know, doing the rest and building the trusses yourself, right? So what this means is that what we're going to do is this is just a basic introduction. I can do this in class, but it's actually a lot easier for you guys just to do on your own with these videos that I pre-recorded and posted to YouTube, right? So I've embedded them here. What you'll find is that the files that I have opened up on my screen that I'm using as demonstrations, you can download here as zip files, right? So you can unzip those files, and then you have those .gh Grasshopper files that you can open up in Grasshopper and follow along or do things on your own if you want, right? But here's the introduction, you know, making a box. Here it is changing the box. Here, instead of making one box, we make a grid of boxes. Here we start talking about making lists of numbers, series, and range. Here we start talking about data matching and cross-referencing, right? And all we're doing is making, in this case, points. Then we start dealing with curves and lines. We start talking about placing points along and finding locations along curves and lines. We start talking about how to divide them, how we start sorting and reconfiguring the information that, you know, in this case, a bunch of division points that we populate along these curves, right? And then for the last set, videos 9, 10, 11, and then 12, 13, 14. So 9, 10, 11, we put all that stuff together and we go through step by step and make that bow truss that I made in front of you guys on day 1, right? And so here's the truss recipe, then we build it, and then I explain, okay, here's what I want you to do for this first assignment. You know, it doesn't take long. Once you have this built and you do it yourself step by step, then you can start to change the parameters around. You capture 3 different instances of the same truss, you know, the same truss recipe, but 3 different variations, right? So if I use the making cookies analogy, right? I would use the recipe and use vanilla extract and Toll House morsels, and we would chocolate morsels, semi-sweet, and we would make, you know, I'd take a screenshot of the resultant chocolate chip cookies. And then I would change the parameters so that then I get peanut butter cookies, and I would take a screenshot of the peanut butter cookies, right? And I change the parameters around and I get sugar cookies. And then I would, you know, take a screenshot of the sugar cookies. So in this case, you have a truss made, and then you can start to alter, let's say, the depth and the shape and the amount of webbing, the density and the size of the tubing and things like that. You know, you do that 3 times and you take a snapshot of each one, and then you upload that just to sort of show me that you're going through the motions of making stuff and then altering it and changing it around with these sliders, okay? And then for 12, 13, and 14, we do something similar. We build off of that. We make a three-dimensional truss, right? So in this case, it's not something flat, but then if you look at it in cross section, it has a sort of triangular cross section, right? So it's like a truss and a truss and a truss, top and two sides sort of welded to make a sort of triangle and cross section, right? But because these are curves and not lines, the cross section sort of, you know, changes throughout, right? And so you'll do these, and again, you'll sort of switch these out and give me three sort of versions, three sort of phenotypes from the genotype, you might say, if you were thinking about it biologically, right? So here's the sort of genome, right? And then I can give you, just like I can, you know, the same genome of a panda gives you 3 different pandas. You know, some have larger eyes, some have ears that are smaller, some are bigger, and, you know, just like humans, you know, any biological, you know, organism, right? If you think about this as developing the graph as a genome, and then I can begin to alter the parameters to generate endless amounts of results, right, of organisms, right? Then that's another way of sort of thinking about this. I'm being heavy on the metaphors here, but we'll continue to rely on those in order to sort of better grasp and understand and visualize what we're doing and why it's important. Okay, right. So I've embedded all these videos here in the Canvas page, right? So you probably noticed, maybe you got a notification. I do on my app, my Canvas app. What I also did here, let me just go back to the modules, is I made 2 assignments, and I put the links to those here in this 25th of August page with all the videos that you're watching in order to do those assignments. But if you go to the modules, let's go to the modules here, right? And go to project 1, you can see that there's 25th of August. You can also see those assignments here. So if you just have 3 screen captures, 3 JPEGs or PNGs, you can go here, right? And then I'll ask you to upload them. This isn't what it looks like on yours. It looks a little different because, you know, let's go to student view, right? It'll say start the assignment, and then I'll ask you to upload files, your three JPEGs or PNG files, sort of screen capturing just the basic Grasshopper stuff you're doing. Okay. All right. Whew. Now, this seems probably somewhat clear. However, over the weekend, you might end up running into questions. I know how this works. It wasn't that long ago. I mean, I'm old and decrepit, but I still remember when I was in school, and things seem really clear in class. But then, you know, sometimes I would procrastinate, or I get busy with other things. And then, you know, on Sunday evening when I'm doing this, I know some of you will. I know a lot of you will actually. You'd go, oh crap, what were we supposed to do again? And no, this doesn't make sense. Or do we do this or that? I'm a little unclear. If you can go ahead and email me. I recommend just emailing me directly instead of using Canvas chat. Sometimes there's a lag in the Canvas chat. But if you do send me a message in Canvas, I will get it eventually. It does pop up on my phone. But you know, again, feel free to email me. But the key thing is just to, you know, again, a lot of the questions I get can be answered by simply going back to the video and just, you know, going back to that specific point in the video and watching it again. You know, in 30 seconds, you can solve or answer a lot of the questions that you have, right? So I might, you know, sometimes I get a little snarky if it's, you know, if it's past 11 p.m. on Friday night, in which case I'd go to the YouTube video and say, just look at this time code and the answer is right here, right? Don't take it personally, you know, just the way it is. But you'll find that I'm actually obsessive compulsive when it comes to getting rid of those silly little numbered red icons on my mail app on my phone. So I am pretty responsive to email when I can be. Okay. All right. And with that, oh, I will say this before I stop the recording. And in class early today. Yay, another sort of yay moment. But I will say next week, we'll talk a little more about, I'll show you some of those silhouette wall drawings, but executed in Grasshopper really quickly, and how you can begin to alter those things. We'll see how things went with the truss and these sort of first set of quick demonstrations and exercises. We'll build off of them. And then I'll also talk a little more about parametric design and architecture. So I'll continue to sort of throw examples at you. So just to sort of, again, make very clear the value proposition here, which is most good contemporary architecture relies on these tools, right? And so, it's not that architects don't sketch or draw or make models anymore, far from it, right? But at a certain point, they're going back and forth between the digital and the analog, right? And they're finding interesting ways to sort of, I would say, do things that they couldn't just do with a piece of paper and trace paper. That's for sure. So, at any rate, I'll leave it there for today, and I'm going to go ahead and stop sharing. I'm going to stop recording.